Hello dear students, welcome you all to the next lecture of the JCE Connect series of online lecture. In today's lecture we will be discussing module 4, which is design of slabs. We will be discussing about a two-way restrained slab. A restrained slab is the one which has its corners held down. That is, it is provided with torsional reinforcement and the corners are not free to lift. So let us start with the discussion. So firstly, from the IS 456 2000, I have taken the clause D1, which explains about the restrained slab. When the corners of the slab are prevented from lifting, the slab may be designed as specified in the clause D1.1. The clause says that the bending moment mx and my, which will be the design bending moments, should be taken as mx is equal to alpha x into w lx square and my equal to alpha y into w lx square only, where w is nothing but wu, which is your ultimate load, and lx is lx effective, that is effective length along the shorter span. Now alpha x and alpha y values will be taken from table number 26 in case of a restrained slab. Then going further, what happens in a restrained slab is the reinforcement which is to be provided is divided into two strips. One is the middle strip and other are the edge strips. This happens along both the spans, that is along Lx as well as along Ly. A detailed description of this is given in clause number D1.2 of IS 456 2000. So next is the different types of slabs as per the IS classification based on the edge conditions. Now edge conditions play a very important role in the design of slabs, because depending on the edge condition the position of the reinforcement will be decided. So here we have 9 cases starting from interior panel, one number, that is all the four sides of the slab are continuous and that panel falls in somewhere locked surroundings. The second one is the one edge continuous, that is the short edge continuous. The third condition is one long edge discontinuous. Next condition what we have is two adjacent edges discontinuous. The next condition is two short edges discontinuous. Next one is two long edges discontinuous. Seventh one is three edges discontinuous, and in that one long edge is continuous. Next condition is three edges discontinuous with the short edge continuous, and the last condition is four edges discontinuous. So always remember while solving this examples based on the restrained slab, if any edge condition is not given, you have to assume that it is condition number 9, that is all four edges are discontinuous, as it is shown in the figure or a box below, where all the four edges for the 9 number slab don't have any continuity on any side. So always remember, if in the example if no side conditions, edge conditions are mentioned, directly go to the condition number 9 for selecting alpha x and alpha y. Whereas if the conditions are mentioned, you have to select the proper condition from 1st to 8th. Then this is the table which will give you the alpha x and alpha y coefficients. So depending on your Ly by Lx ratio, you have to select the proper edge condition and select the proper alpha x and alpha y value. This will be more clear when we solve one example. So now let us start with a design example for simply supported two-way slab with corners held down. So the example goes like this. Design a simply supported slab for a panel of size 5 meter by 4 meter, supported by 230 mm thick wall. Use M20 and Fe 415. The slab supports a superimposed load of 4 kN per meter square. and a floor finish of 1 kilonewton per meter square. The corners are held down. So let us first note the given data. Lx is equal to 5 meters. Lx is equal to 4 meters. Ly should be 5 meters. Please make the correction. Support width is 230 mm. FCK is 20. Fy is 415. Live load is 4 kilonewton per meter square and floor finish is 1 kilonewton per meter square. So let us start with the check. Ly by Lx, the longer side is 5 meter, shorter side is always Lx, which is 4 meter. So we get a Ly by Lx ratio of 1.25, which is less than 2. Hence we have to design the slab as two-way slab. So now what happens here is we have to go for a design of two-way slab, but the edge conditions are not mentioned clearly. Hence, as I told you earlier, we have to refer condition number 9 for taking the coefficients alpha x and alpha y. So we have to read the example carefully. As it's a restrained slab but no edge conditions are mentioned, it indicates that you should refer ninth condition of the IS 456 code book table number 26. So further in the example we'll come across it. So first step, this is a common step wherein we'll be fixing the dimensions. So what we have done here, on the right side is the reference of the IS 456 code book, which says that effective depth for simply supported slab will be shorter span divided by the 20. Okay, D is equal to Lx by 20. But what we do is practically, let us adopt L by 25 as the ratio and we get depth as 160 mm. Then the effective cover is assumed as 20. So the total depth of the beam comes out to be 180 mm. Further, let us fix the effective length. Now as it is a two-way slab, the effective length needs to be fixed up in both the direction, that is we got to fix up the length in both the directions, that is Lx effective as well as Ly effective, using our regular formulas from IS reference. Effective span along the x direction, that is the shorter span, is clear span plus effective depth or center to center distance between the support, least of the two. So here we can say that the effective length is 4.16 meters. Similarly, along the longer span, we get an effective length of 5.16 meters. So let us find the effective length ratio R, which is Ly effective upon Lx effective, which comes out to be 1.24 meters. Now these all steps are basically repeated from your beam design onwards, and hence you should be able to do all these steps very fast. So next comes the step of load calculation. So as repeated earlier, always remember that for slabs you have to find the load considering 1 meter width of the strip of the slab. Hence B in all calculation will come out to be 1 meter or 1000 mm. So let us go ahead with the load calculation. Self weight, floor finish, imposed loads. So these are the three loads which we need to calculate. So self weight is nothing but the total depth into density of the slab multiplied by 1 meter. As I said, we have to consider 1 meter width. Okay, because we designed the slab for a strip of 1 meter width. Similarly, for floor finish, let us multiply by 1 meter, then the imposed load, which is the given data. So total load we get as 9.5 kilonewton per meter, which is in the form of UDL. So now let us multiply this load by a factor of safety of 1.5. Hence we get a factored load WU is equal to 14.25 kilonewton per meter. Again, this step is very much similar and easy. So now comes the important part of the restrained slab, calculation of the design bending moment. So when we refer page number 91 of IS 456-2000, this clause was discussed in the earlier discussion. d 1.1, mx is given by alpha x into w lx square, and my is equal to alpha y into w lx square. So one more thing again I want to repeat here is, in both the calculation only the changes alpha x value and alpha y value, else w and lx remain the same. Don't multiply here by ly, else your sum will go wrong. So as no edge conditions are given, which case we have to refer from table number 26? Yes, we got to refer case number 9 from table number 26, as there are no edge conditions given. So let us take the values of alpha x and alpha y. Now here the table is clearly visible to you all. For our alpha x Ly by Lx effective ratio of 1.24, we will be selecting alpha x and alpha y values between 1.2 and 1.3. Okay, for 1.2, what is the alpha x value? 0.072. And for 1.3, okay, so here you have to check out 1.3. For 1.3, what was the value? 0.079. Then our effective Ly by Lx ratio is 1.24. Hence, by interpolation we can find alpha x. So now in this case alpha y can be directly taken, as there is no different values. Directly the alpha y value can be taken here, that is 0.056. So alpha x by interpolation we get 0.075, and alpha y we have to keep as it is. Now this is how we got to find the values of alpha x and alpha y for our slab. Bending moment along both the spans. So let us go ahead with the calculation of bending moments. Mux is equal to alpha x into wu into lx effective square. Muy is equal to alpha y into wu into lx effective square only. So substituting the given values, we get mux is equal to 18.5 kilonewton meter and muy is equal to 13.8 kilonewton meter. So what you have to remember here is, always you will get the bending moment along the shorter span with a higher value. If you get muy higher, then you have made a mistake somewhere. So this is one checkpoint for you all, where you have to see that the mux value is greater than the muy value, because the slab bends more along the shorter span as considered to the longer span. Now let us go ahead and check out the depth which we have provided is sufficient or no. Okay, let us go ahead and check out whether the depth which we have provided is sufficient or no. So for the check for the depth of Fe415 grade of steel, D required is equal to square root of mu upon 0.138 FCKB. So let us take mu value as 18.5, which is the higher of the two, because if the given depth is able to satisfy the higher moment, it will of course satisfy the lower one. So substituting the values, we get D required as 82 mm. So we have provided 160 mm, which is more than sufficient than the required. This is only as per bending consideration. Further, when we take deflection and all, a higher depth will be required. Don't think that 82 is required, we are providing 160. Only bending doesn't govern the design criteria. There are other factors also which have to be taken into consideration. So this depth provided passes in this check. Hence we can conclude that the section is safe. Going further, now this is the most important thing of your design of a restrained slab. The reinforcement needs to be divided along two parts or two strips, that is the center strip and the edge strip. I have shown with the hatch marks the center strip as well as the edge strip. So width of the middle strip is 3.87 and width of the end strip is 0.645 when you consider the shorter span. Okay, when you are considering the shorter span. Then when you consider the longer span, okay, width will be 3.12 and end width will be 0.5. phi 2. So here you have to be careful while taking the strips. So when we take the bending along shorter span, the longer length will come into consideration, and when we take the bending along longer span, shorter length will come into consideration. So don't get confused. Okay, these are taken from IS 456 codebook. So let us find area of the reinforcement along shorter span. Okay, area of the reinforcement along shorter span where the longer length will come into picture. So what happens here is, for the middle strip we say is AST x required. Substituting the values in this formula, you have to practice substitution in this formula, which is very much important. MUX value we substitute and we get AST required as 335 mm square. So selecting 8 mm diameter bar, we get a spacing of 150 mm center to center. So when we compare with the IS 456 regulations, this 150 depth is least of the three options available to us. Hence let us provide 8 mm diameter bars at 150 mm center to center as main reinforcement along the middle strip for shorter span. Then for edge strip along shorter span, what we have to do is we can provide AST is equal to AST minimum itself. Okay, we have to provide AST is equal to AST minimum itself. So what we have done here previously, we have already in the last line we have calculated AST minimum and kept, which is 0.12% of BD. Okay, this we have calculated 216. Now this 216 we are directly using it here and providing it as reinforcement for the edge strip. Reinforcement for the edge strip. Going further, the area of reinforcement along the longer span. Here we have to substitute the value of MUY. So when we substitute the value of MUY, we get AST required as 247 mm square, which is of course greater than AST minimum. Again using 8 mm diameter bars, we get a spacing along the middle strip longer span as 200 mm. Rounded off, we can take 200 mm spacing for the middle strip reinforcement along the longer span. So again for the edge strip we can use AST minimum. Okay, once we use AST minimum we get a spacing of say 232, but let's provide a spacing of 230 mm center to center for the edge strip reinforcement along the longer side or the longer span. So here I have summarized the reinforcement provided from the design along the longer span, along the shorter span, both are given. I think again I have made a mistake. The 150 mm steel should be along the shorter span because it is more, and second one should be along the longer span. Please excuse me, make a note of it. First is the shorter span middle strip, then second one is the longer span middle strip, because shorter span is bending more than the longer span. Then this is the next step, which is there only in case of the restrained slab. What is the step? In this step we provide the torsional reinforcement. It is as per IS 456-2000 page number 90. We have to provide this reinforcement in the size of a square mesh, and the size of the square mesh will be Lx by phi. So what is Lx? Effective length in x direction, which is 4.16 meters divided by phi is equal to 0.832 meters. Say let us assume it as 0.85. So we have to provide a square mesh of size 0.85 by 0.85. So we have to provide this reinforcement in the form of a square mesh of 0.85 by 0.85, and the area of the reinforcement as per IS 456 will be 3/4 of ASTX provided, which we have already calculated previously. ASTX provided we have calculated as 335.1. So 3/4 of 335.1 comes out to be 251.325. So selecting 8 mm bar diameter as main reinforcement, we get spacing is equal to 200 mm. So for torsion, that is in case of a restrained slab, we will be providing a square mesh of size 0.85 by 0.85 meters, and the diameter of the bar used will be 8 mm, and spacing for that strip will be 200 mm center to center. So this is what is required in case of the design of a restrained slab, that is corners are not free to lift but no edge condition is given. So directly we are using case number 9. So in the next example, so we will try and discuss one more slab design with some edge condition so that we can complete all the required things in the slab design. Thank you very much.